Parallel backout. Parallel backout occurs when there is a prolonged swelling and shrinking of the timber over time, slowly pushing the nail plate out of the timber. Tapered backout. Tapered backout is again caused by the swelling and shrinking of timber over time, this time pushing one side of the plate out while the other side moves with the timber. Curling or peeling. Curling or peeling can be caused by two issues. One is the overloading of the member, causing the nail plate to slowly push out under duress. Curling can also be attributed to the swelling and shrinking of the timber over time. Heaving. Heaving is a manufacturing issue and occurs when the nail plate is used to pull the two pieces of timber together. This eventually causes the nail plate to warp and pull out over time due to the opposing forces. Doming. Doming is caused by the shrinkage of the timber on a vertical plane, causing the plate to bend out. Alignment. Alignment problems can be caused by defective manufacturing practices during installation, and also the warping of the timber members. Cupping. Cupping in the nail plate is again one of the many problems that can arise from the shrinking of the timber. Pairing. Pairing is caused by the swelling of the timber leading to the closure of the joint. The nail plate starts to bend at its centre due to the opposing forces. Bulging. Bulging is caused by the handling of the nail plate and poor installation practices. Thickness. Thickness issues are caused by poor installation and poor design.
Hello, I'm Mohamaad Anisur Rahman and we'll talk about investigation techniques for backout of nail plates from timber trusses. Nail-plated timber roof trusses have been widely used in Australia for more than half a century. In 2002, the fall of a double-girder truss at a clubhouse in Adelaide, killing 2 people, triggered the necessity of investigation of nail plate backout on timber trusses, not only for the existing trusses but also to predict possible future failures. Investigation techniques for nail plate backout on timber trusses can be categorized into 4 methods, which are numerical modeling, laboratory testing, field studies, roof and timber truss inspection. We'll start with numerical model. Numerical modeling can be conducted in 3 ways as identified by Perry et al. First of all is climate microclimate wood interaction model, which predicts the swelling and shrinkage of wood inside a roof space considering fundamental building physics and site factors, that is external climate history including temperature, humidity, rain, solar radiation, cloud cover, wind speed, etc. Then finite element model. In this model, an idealized single tooth of a nail plate is inserted in a wood member where mechanical forces acting on the tooth are investigated as shown in the picture. Here the variables are Kf, which is the total side friction resistance acting vertically in both directions, and Kc, which is total end crashing resistance due to clogging of the tip space and rebound of the wooden fibers underneath the fastener tip. The last one is the simplified analytic model, where a simple spreadsheet software such as Microsoft Excel is used to predict fastener backout for given time history of wooden swell shrink and for given friction and crushing characteristics of the nail plate. The example in the figure shows and output for prediction of first and backout over 40 years. Laboratory tests are done through either wetting and drying test or mechanical press pull test. In wetting and drying test, nail plate backout due to swelling and shrinkage of timber can be determined through wetting and drying exposure under defined moisture cycling regimes, mechanical loadings and sealant treatments, whereas in determining the crushing and friction characteristics of the nail plate teeth and to use it in simplified analytic model, mechanical press pull tests are conducted. Here the significant variables that are considered are the length of the force withdrawal, grain direction and exposure conditions, etc. To monitor the relation between microclimate, for example, the effect of conventional roof circling and the nail plate backout, field tests are set and conducted. In this method, monitoring of climatic data is conducted in certain frequency of time for a certain period of time. For example, data is collected in every 20 minutes for 1 year. Here the significant variables are outer air temperature and relative humidity, rainfall intensity, global solar radiation, wind speed and direction, indoor air temperature and relative humidity, air temperature and relative humidity in the roof space, etc. In this method, to capture the climatic data, scientific wireless weather station, independent sensors with data loggers, data logging systems in PC, thermo-hydro sensors, etc. are usually used. Roof and truss inspection. In general, Australian Standard 4399.1 provides the method of inspection for residential buildings, and Minister's Schedule 5 of the Development Act 1993 provides a checklist for roof framing. Beside those, while investigating nail plate backout in timber truss building, irrespective of the class of the building, the following must be checked. Existence of gutter trusses, to which extra attention should be paid during the inspection. Nail plates must be in tight contact with the truss members. If there is any gap, it can cause a future structural failure. Heel joints and internal support points must be checked. Any alteration to trusses and truss bracing must be checked. Whether there is any water penetration in the roof, any damage or dents in the ceiling cornice indicating truss movement. Truss timber quality should be checked. There shouldn't be any knots, splits or large cracks near the joints. There shouldn't be any truss sagging and corrosion of metal fasteners. Truss bottom cord must be adequately restrained and clear of non-load bearing walls.
Factors affecting nail plate separation. The main factors which cause failure of the nail plate can be summarized as follows: mechanoabsorptive effects, overloading, handling errors, manufacturing errors. The effect of each of these factors will be discussed in the following slides. Mechanoabsorptive effects. In unsarc tile roofs where water penetrates through roof tiles, the amount of moisture or humidity varies in the roof space over time. This will cause the wooden roof frame to swell and shrink repeatedly, which is called moisture sucking effects. As a result of this ratcheting mechanism, withdrawal deformation accumulate and the nail plate backout occurs. The sources of water penetration and their effect on the nail plate backout in unsarc tile roofs has been discussed in the following slides. Humidity cycling. Long-term daily humidity fluctuations can cause structural failure of nail plates in very highly loaded joints as a result of the significant levels of backout. In sarc roof, humidity-driven backout can be reduced by as much as 70% compared to unsarc roof. Leaking. Roof leak through cracked or broken tiles is another source of water penetration in unsocked tile roofs. Joints which are loaded more than 70% of their design capacity and are subjected to repeated wetting from roof leak are more susceptible to significant backout under cycles of wetting than are joints with small loads in the same environmental conditions. Wind-driven rain. Only light rainfall events are likely to have an effect on the nail plate backout. Light rainfall event is defined as less than 1 mm rainfall in 30 minutes. These events are more frequent in Adelaide than in Melbourne, Sydney, or Brisbane. Wind-driven rain can penetrate an unsocked roof space, especially if the tiles are loose-fitting or cracked or broken. Overloading. Highly loaded joints are those joints which carry more than 70% of their design load. These joints can potentially fail to rupture on the small number of cycles of wetting and drying, which is less than 50 cycles. In the following slides, some example of the main causes which make the joints to be overstressed has been discussed. Misplaced nail plates. When the nail plates are misplaced, one side of a joint will be overstressed. An overstress by about 30% from this cause would not be unusual. Air movement. The effect of air movement on the joint can considerably increase the deformations obtained due to the increased drawing for each humidity cycle. This is likely to occur near the heel of a truss in an unsocked roof, particularly if the heel is located above an open wall cavity. Under-designed nail plates. Nail plates which are under-designed will carry larger loads than appropriate. As an example, many of the problems observed in South Australia related to Sealfast brand nail plates in many cases were under-designed nail plates. Manufacturing errors. Nail plates which are not fully embedded is one example of errors in the manufacturing process. Handling errors. Lateral movement across the joint can occur as a result of inappropriate handling of the trusses in the manufacturing plant or during transport, storage, and/or installation.
Remediation methodology for nail plate backout on timber trusses. This presentation will concentrate on the processes involved when nail plate backout is detected on timber trusses, the industry standard method of repair, and where necessary, the subsequent maintenance. In consideration of the technical skill and severity of risk associated with truss failure, it is recommended that a suitably qualified engineer should be appointed to assess and determine the extent, causation, severity of nail plate backout, and if necessary, provide a remediation scope of work and/or make safe to mitigate harm or further damage. A remediation scope of work is likely to entail preliminary works whereby roof coverings and other removable loads items are evenly removed, unloaded from the subject defective trusses. Nail plate backout could be addressed by using a couple methods. The first, option 1, by repressing the backed out nail plates to their originally factory impressed position and then providing screw fixings to retard future nail plate backout. Option 2, on the other hand, is a more in-depth and somewhat parasitic structural remediation method that involves the appointment of an engineer to design and prescribe the installation of plywood gussets that will supplement the faulty deficient nail plates, ensuring the transfer of forces into the appropriate members. The installation shall be carried out by a suitably qualified contractor, preferably a carpenter. Option 2 example. Heel ply gusset detail designed by an engineer and installed by a carpenter. Typical materials include Tech screws, F17 plywood of subject depth and thickness, hardwood edges, high strength construction adhesive. The heel is considered to be one of the two most significant connections, with the apex being the other. Option 2 example, web to top chord typical plywood gusset detail. Once again, it's designed by an engineer and installed by a carpenter using the same method and materials as previously mentioned. Option 2 example, web to bottom chord typical plywood gusset detail designed by an engineer and installed by a carpenter using the same method and materials previously mentioned. The plywood gusset is curtailed for cosmetic purposes only. Option 2 example, apex plywood gusset detail designed by an engineer and installed by a carpenter using the same method and materials previously mentioned. The connection is integral of typical standard trusses structural adequacy. Another option 2 example, truncated truss connection using the typical plywood gusset detail, designed by an engineer and installed by a carpenter using the same method and materials as previously mentioned. The plywood is curtailed for cosmetic purposes only. The associated labour and therefore cost to remediate nail plate backout is likely to allow for engineering and their auxiliary services as required, such as drafting details and scope of works. Further involvement of the subsequent trades is likely to flow through to electricians, roof plumbers, general tradesmen, carpenters and painters. In consideration of the appointed engineer's make-safe causation report and all remediation works, a responsible asset manager should ensure the implementation of a scheduled program maintenance or, if necessary, truss replacement as prescribed by the appointed engineer.